Okay, so let me show you how we apply Hess's law.
Okay, so we need to work with individual reactions. We know for little reactions, simpler reactions, we know their delta H, so how much, or delta H molar I should say, how much energy is involved in a reaction per mole of a certain substance. So the first rule is, if I have to reverse my reaction to kind of suit my needs, well, if I'm looking at the opposite process, I have to look at the opposite amount of energy as well. So let's say in my example, I don't need this format of this reaction, but I need the opposite. So it's kind of flipped around. Well, if I flip my equation, I need to flip the energy as well. So I'm going to go from a negative to a positive. The same amount of energy will be involved, but rather than being exothermic, it'll be endothermic in this particular example. Secondly, if to suit my needs, I need to multiply my equation by a certain coefficient, well, in that case, I need to also multiply the amount of energy involved by the same coefficient. So in this example, everything got doubled. So I went from C to 2C, O2 to 2O2, CO2 to 2CO2. Well, obviously, I need to also double the amount of energy involved in this newer version of the reaction. So now, how does this get applied to an actual Hess's law situation? So I have this equation here, and I want to know what is the delta H molar, the amount of energy involved in this reaction. This is not necessarily observable and happens too fast, but I know slower processes that, if added up together, will give me the same exact equation. So based on that knowledge, I will be able to determine the missing value here. So I know that this process here releases this amount of energy, and this reaction here releases this amount of energy. So I need to kind of add up these two steps in order to obtain this and figure out how much energy would be involved in this particular system. So the first thing you can do, there's different ways of approaching this. I'll show you one longer way, and then I'll show you the faster, shorter way for those of you who are comfortable with the concept. So first, I want to locate the substances in my individual reactions that do appear in my final or whole reaction. So I need to find my carbon solid. So if I'm looking for carbon solid, I have to box in a carbon that is solid. If it was a gas or liquid, it's not the same. So I want exactly the same thing. So here I have a carbon solid. Okay, so I need that. O2, I have it in my final reaction. CO2, I don't. So I don't box it in. I don't want to keep it at the end of the whole exercise. Here, CO, I need it over here. O2, I need it. I have it here. CO2, I don't need it. For now, I'm just boxing in the right molecules, regardless of how many I have in my individual steps. Okay, so I just want to match my substances. I need some O2, I'm looking for O2. I need some C, I'm looking for C, so on and so forth. So that's the first step. The second step is to then verify if those items that I boxed in are on the same side as in my final reaction. So I have, for example, carbon here is on the reactant side. I do need it on the reactant side, that's fine. Oxygen, because I have it in two places, I won't bother with it. The chips will fall where they may or where they need to if I deal with the rest. So let me not bother with oxygen. I'll deal with substances that are present only in one equation, one place. So here I have 2CO. I need the CO on the product side, but I have it on the reactant side, which means I'm going to have to rewrite this equation, but flip it instead. And if you remember from the previous step or the previous page, I said, if you flip an equation, you have to change the sign of the delta H as well, because you're looking at the reverse reaction. So let's say it was exo before, it now becomes endothermic. So let's go back to the example. So this one here, number 2, I have to flip it. So I rewrote here the equations in the right format. So the first one I kept as is, but the second one I flipped over. So my CO2 is now on the reactant side. My CO is now on the product side as well as the oxygen. Because I flipped it, I changed the sign. Now it's positive rather than being negative. Okay, so now I have two steps. I located my substances, which ones appear in the original or final reaction, whatever you want to call it. And then I flipped whatever I need to flip, including the sign of the energy. Third step, I need to verify if my coefficients match what I need in the final answer, the final equation. So if I go back, carbon, how many do I need? I need only one. So there's only one carbon here. I need only one in this equation, which is what, which is what I have. I have only one carbon. Again, oxygen, I'm not going to look at because it's in two separate places. I'm going to deal with that at the end. Let's look at the CO. How many COs do I need? I need one CO on the product side. So if I go down a little bit, okay, so I'm just going to look here. I have two COs, but I only need one, which means I need to divide the whole line by 2. That is why over here I crossed it out and I rewrote the same equation, but with all coefficients being halved. So I went from 2 CO2 to 1 CO2, 2 COs to 1 CO, 1 O2 to half an O2. So now my substances are on the correct side of each equation, and they have the right coefficient. And by the way, let's not forget, since I divided the whole line by 2 here, I needed to divide the delta H over here by 2, which gives me plus 280 kilojoules. Now, finally, whatever I'm left with, I'm going to add up. So they're rewritten here again with the proper delta H molar. So I'm adding up everything. So everything gets rewritten on both sides. And then whatever appears on both sides cancels out. So this here and this here will cancel out. I have the same amount and it's present on both sides. Now here it's a little special. I have one O2 on this side, but I have half an O2 on this side. So this one will disappear, but this one will not disappear completely. I'm going to be left with half a molecule of O2, which is what I have here. So my C stays, it doesn't get canceled out, right? So C is over here. Here I'm left with half an O2 because only half of it gets canceled by this on the other side. These two disappear and this over here stays and goes over here. So what do I end up with? I end up with the same reaction as I had initially if we look on top. This is what I needed. C plus half an O2 gives me CO. That's what I obtained. C plus half an O2 gives me CO. But the beauty of this is that now not only did I add these up to get my final reaction, but now I can add these up over here to get my energy for that process. So it gives me my delta H molar for this process, which is negative 110.5 kilojoules. Here I should say, per mole. And I could say per mole of carbon, for example, because there is one carbon. Okay? So that's it for that. So now we're going to look at two examples. I'm going to solve them with you, for you. And I will do it the faster way. Okay, so here we go. I have CH4, 2O2, CO2, plus 2H2O. I want to know the amount of energy involved in this reaction. Okay, so here I have to box in whatever I need to keep. So I need CH4. Where does CH4 appear? I have it here and nowhere else. O2, I have it here and I have it here. Okay. CO2, I have it here. And H2O is over here. So I have all this stuff that's going to disappear eventually. Now, let's see if my substances are on the correct side. My CH4 is on the product side. I actually need it on the reactant side, which means I'm going to have to reverse this equation. Reverse, R for reverse. Okay, then O2 being in two places, I'm not going to bother. looking at it, CO2 is on the product side. I need it on the product side. That's fine. H2O is on the product side. I need it on the product side. That's also fine. So these don't need, the next two don't need to be reversed. Let's now look at the coefficients. I need 1 CH4. I have 1 CH4. I'm fine. I don't need to multiply this line. I need 1 CO2. I have 1 CO2. I don't need to multiply the line. I have 2 H2Os, but I only have one here. So that means I'm going to have to multiply this line by 2 in order to get the coefficient that I need for H2O. So I'm going to end up with 2H2, 2 over 2O2, which is really 1O2, and 2 H2Os. Okay, now let me also rewrite this since I need to reverse it. So this is going to become positive, and this is going to become CH4, arrow, C solid, plus 2H2 gas. Okay, so now if I add up everything I have CH4, I have carbon, this is gas, I have, what else, 2H2, gas, and I have 1O2 plus 1O2, 2 O2s. Okay, on the other side I have carbon solid. I have 2H2 gas. I have CO2 and 2H2O. Okay. Now next I'm going to cross out whatever is on both sides. So I have carbon and carbon. I have 2H2 gas with 2H2 gas. I have nothing else. So I'm left with CH4 gas plus 2O2 gas gives me CO2 gas and 2H2O gas. Now, is this what I was looking for? Yes, it appears to be. So I know I did my job right, therefore my energies should add up and give me whatever I'm looking for. So I would do plus 74.6 minus 393.5 plus this value times 2. So this is negative, right? So I say plus this value times 2, but really it becomes a negative. So if I rewrite it, I'm going to have 74.6 minus 393.5 minus 241.8 times 2. And that will give me my delta H for this whole process, which happens to be 802.5 kilojoules. I could say per mole of CH4, for example, because there's only 1 mole of CH4 in here. I could also say per mole of CO2 if I wanted to, same difference. Okay, so this way, the technique I used is not quite the fastest because I did rewrite a few things just to verify that I would obtain the correct equation at the end. So to make sure to kind of prove that I did my work right. Now you could do it even faster, which I will show you in the second example. So whatever you feel comfortable with, you may use. You can do it the very long way and rewrite everything, all the equations. You can do it halfway the way I did, or you can do it the following way. So I'll show you the super fast way. So if you're very self-assured, you can do it this way. Okay, I need C4H10. It's on the other side. Coefficients are the same. All right, so all I need to do here is reverse and not multiply. Next, I need carbon 4 times. It's not anywhere else but here. So this is on the correct side. It's on the reactant side, but I need it 4 times. That means I'm going to have to multiply this line by 4, but not reverse it. And I need some H2. Where's my H2? My H2 is only here. It is on the correct side because it's on the reactant side and that's where I need it. But I only have a coefficient of 2 and I need a coefficient of 5. That means I would have to multiply this line by 2.5 to get that. So times 2.5 will give me 5H2. So now all I need to do is say plus 657.4, because I reversed the sign, plus 4 times negative 393.5 plus 2.5 times negative 483.6. That will give me my delta H for the reaction. So you can choose to do it that way, that's all good if you're super comfortable with the approach, but you won't know if you made a mistake. So if you do your calculation like this, or regardless of which way you do it, you should get an answer of negative 125.6 kilojoules for the delta H. Again, if you want, you can write it as delta H molar, and if you do write it as delta H molar, so we say it's minus 125.6 kilojoule per mole. Well, I have 1 mole of what in here? I have 1 mole of this. So in this case, I don't have a choice but to say per mole of C4H10. There you go. So that's it for Hess's Law. Hopefully it's all nice and clear. Otherwise, you can see me in class if you have questions. Ciao!